So what step were we on? That was step 3, where we convert it. Step 4. Once converted, do the new integral. Actually, I'm skipping what I think of as an important step. Once converted, is this problem easier? Remember, our setup here isn't a place where we're following an algorithm to a conclusion. We're trying a trick and see if it works. Give yourself a chance to breathe and see if it worked. If we did a substitution that turned our original problem into a much more difficult looking problem, we don't have to keep going in this direction. Go back to the last one and try something else. This choice of u we made is often going to be a bad choice a few tries before we find a good one. This is a place where we did a good choice, so yes, if I look at the original problem was integral of cosine x sine x, the cosine and the sine stuff is gone. This is a simpler problem. But do this step. Check if you actually have made it better. If it's not, go back and try something else. And then step 5, do that integral. I said that like this is the last step. It's not the last step yet. I've got the integral of e to the u du. Do I know how to integrate that? Yes, I do. The integral of e to the x is e to the x. The integral of e to the u is e to the u. Plus c. This is the one where it happens to be the same answer. Usually you don't have the exact same answer. Once you've done that integral, you need to convert that answer back into x's using the formula you wrote down. If you've done this a bunch of times, you might have lots of different u equals written down. Make sure you're using the u equals that was relevant to this attempt. We had u equals cosine x. This answer that it's negative e to the u says that that turns into, come on, negative e to the cosine x plus c. And there's a correct answer, and that's what it was supposed to be. A way to think about this is doing French math problems. How do you do a French math problem? Most of the time, or if you're not French, the answer is you translate the problem into English, you do the problem in English, and then maybe you translate your answer back into French. And that's kind of a way of thinking about what these steps were. This U is an attempt to translate the original problem, which is written in hard language, into something that is hopefully easier for us to do. So this was translating the problem from an X problem into a U problem. Now you have to do the U problem. A lot of students forget to actually do the problem once they've translated it. This doing the problem step is hopefully the type of integral that we know how to do, but it might be something that needs more tricks. There will be situations where you do a substitution and find out you still need to do another substitution. The tradition is to go from U to V to W if you need more letters. And then after you've done the problem, you translate it back. Translate, do, translate back. That's the idea of integration by substitution. Let's do some examples. Let's try the integral of 5x over x squared plus 3. So, step 1, or I guess step 0, do we know how to do this? No, I can look at my list of things I know the integral of. This is not any of those categories. Step 1, I gotta pick a u thing. This is the place where, in a lecture, I would say, hey, do you guys have an idea for a u to try? And I have written down here the suggestion I got last time, which was, we want u to be something that we see on the inside, whose derivative we kind of see on the outside. When I taught this last, someone suggested let's try u equals x. So let's try that out. If u equals x, then what's du? The thing we're doing is start with what's du dx. What's the derivative of u? U is x. What's the derivative of x? It's 1. So du dx is 1. Move that dx to the other side of the equation. Du is 1 dx. Okay, now let's make our substitution. 1 dx is just dx. Dx is just du. Converting this to a du is easy. That becomes now du. 5u, what does that become? Well, x is u, so that can become 5u. And x squared plus 3, what's that going to become? Well, x is u, so I can rewrite that as u squared plus 3. So altogether, I've written every part of the original problem down. The problem becomes 5u over u squared plus 3 du. We did the doing the substitution step. What's next? Step 2, find du. We did that. Step 3, convert the integral. Make sure there's no x's left. There's no x's left anymore. This is an only u integral, so we would be allowed to do it now. Step 4, is this better? Is this problem look easier than the original problem? No. This is actually the exact same problem with u's instead of x's. It's not just the exact same difficulty, it's the exact same problem. What? Here's a heads up. U equals x will often feel like a good substitution. It's a trap. U equals x is rewrite the problem with u's instead of x's, which is what we wound up doing. The derivative of x is 1, so du ends up as dx. Well, yeah, because u and x are the same letter, so du just changes to dx. When I was learning calculus, I walked into this trap over and over and over again. You sort of gotta get the hang of stop doing that. U equals x often looks like a good idea. It never ever does anything. It's just switch the letters out. So that didn't work. This is a place where a lot of students get really frustrated and say, why did you write this down? Why are you showing me the wrong way to do it? Just show me the right way. Well, this is a thing you do by trying it a bunch of ways. There's only so much you can learn by doing it. Like on the exam, you're probably not going to do everything the right way the first time. You got to get you learn to avoid these mistakes by making them. 5x over x squared plus 3 dx was our original problem. Let's try something else. Let's try u equals... Oh, and by the way, if you're in a situation where like that thing took up the entire page, you might want to pick a different letter, use v instead of u. If you're writing u's, make sure you put a little tail on them so that they don't look the same as your v's. I'm going to go ahead and use u because I'm on a different page and I don't think I'm likely to mix myself up. Okay, let's pick a new thing as a u. I want a u that's stuck on the inside, whose derivative I kind of see on the outside. One choice is x squared. Think about what is the derivative of x squared. The derivative of x squared is 2x, so du will be 2x dx, and I kind of have this x is touching that dx, right? Like these are things that are all multiplied together. I have the x and the dx touching each other, which is great. There's a fundamental tension where I want to make my u something really big, because the more I soak up with the u, the simpler the new problem will be. But usually, when I make a really big u, I'll get a really big du that's not all there to solve. I'm running out of time right in the middle of a thought. Go straight to the next video.